We're going to talk about why we should study C and where the language came from. We're going to talk about the different standards of the C language that are out there. And then we'll roll up our sleeves and get started. We'll look at some basics. We'll look at the Hello World program, and we'll talk about identifiers and intrinsic types. So why should we learn C? Well, first of all, it's important to realize that C is a very widely used portable high-level programming language. It's used in many different systems, and it's been around for a long time. It's high level, but it also lets us program very close to the metal, so we have more control over the underlying machine or hardware than a lot of other high-level programming languages give us. Therefore, it's increasingly important for embedded programming. And furthermore, many languages out there actually are based on C. So they have a C pedigree. Languages like Java and C# and PHP and many other languages actually borrow a lot of the syntax and semantics that originally appeared in the C programming language. And finally, if you're a GVSU computer science student, you're going to see more C in some of your upcoming courses. So courses like CIS 452, and occasionally there's special topics courses that use it, 459, and others. So where did C come from? Well, it was originally developed by a person by the name of Dennis Ritchie at AT&T Bell Labs way back in 1972. And you can see some pictures there of Ritchie. And there's also another person I've got here, Brian Kernighan. And although he didn't actually write the language, he was very involved. He was a co-author of the kind of classic C book that a lot of people refer to as the K&R C book, and I've put a screenshot of the cover there that you can see. So he co-authored that book, and a lot of us learn C for the first time by reading that book. And as I've mentioned already, C has had an enormous influence on other modern programming languages. Well, what about the standards? Well, first of all, there was the K&R C, and this was essentially C compilers that were inspired by that very first publication or description of the C language, so the K&R C. And later ANSI standarded it, and today we know of this, or we refer to this as the C89 or C90 specification. And ANSI C is going to be your most portable version of the C language. So if you want to use your code on different platforms, you're really going to want to aim at ANSI C. And most compilers will let us turn on ANSI C mode by using the -ANSI or -standard equals C89. And then there's C99, a more recent version of the C language that extends the C89 C90 specification. It adds some new data types, and it also adds support for variable length arrays. Now, by default, the GCC compiler that most of you will be using is going to default to the ANSI C version. So if you don't specify anything, you'll end up using ANSI C. And that's what we're saying here. You can read about some of the C99 extensions by following the link I have here. There's some other interesting options. For example, if you want to see warning messages, more warning messages, you can put a -pedantic when you compile. And then finally, on the GNU compiler, you can also put a -std equals C99, and you will get some of the C99 features, but not all. All right, great. So that was a quick overview of the C language. Let's take a look at some code. So here's our obligatory Hello World. We always introduce new languages by looking at a Hello World program. And in this fragment, you can see up top the #include. This is referred to as a header file, and this one is the standard IO or stdio.h. And this is basically a header file that defines all the standard input and output routines that our program is going to use. Secondly, we can see this main function here. It returns a int, that's an integer value, more on that in a moment, and it takes as an argument void, which in C means there are no input arguments to this program. So main is the entry point. In other words, when we compile and run this program, main is where the runtime is going to start executing. The first statement in our program, so the main is followed by a block, which is delimited by the open curly, close curly. And the first statement here is a printf statement. And what printf does is it prints out whatever we tell it to what we call standard output. And we'll talk about that more later. But basically, if you run this program from the terminal window, it means it's going to print out whatever we put inside the parentheses here to the terminal window itself. And you can see what we're printing here. It's just a string value, hello world, and you might have noticed this /n on the end, and it might have looked quite strange, but basically it's just an escape character that means new line. So we want a new line to be added after this text is printed. Finally, the last thing our program does is it returns a 0 to whomever called it. And we have to do that because we defined the main routine originally as returning an int. So we have to be sure to return whatever we said in our function prototype that it was going to return. So let's talk about the basics here. How do we name our variables? Well, here's some simple rules that you can use. First of all, your variables or identifiers must begin with a letter or an underscore. That can be followed by any combination of letters, digits, or additional underscores. But of course, you cannot use a reserved word, a word that's actually defined or used in the actual syntax of the language. So here's an example of some valid variable names or identifiers. Okay, so all of these either start with a letter or an underscore, and after that contain either digits, letters, or underscores. And you'll want to note that just like in many programming languages, these variable names are case sensitive. So in the second to the last, when I've got a capital C there, I've got what we call camel case, test case there. That is actually different than a variable name that had a lowercase c. Here's an example of some variables that would be invalid. So one at last is invalid because the @ symbol is not allowed in variable names in C. 3 underscore times is not allowed because we cannot start variable names with a digit in C. Char, C-H-A-R, is not allowed because that, as we'll see in a moment, is actually a reserved word. It's a type definition in the C language. First space name would be illegal because we cannot have a space in a variable name. So all of these are invalid. What about data types? Well, let's talk about some of the intrinsic or built-in data types in the C language. First of all, we have the char data type, or some people say char. And what this is a character data type. Typically, on most machines, we're going to store, or it's going to be stored in a single byte. And you'll see I've got some literals, A, B, C, and 2. So characters, when we do character literals in our programming, in our C program, we're going to delimit it with a single tick character. We also have support for integers, and that is the int type. Now these typically define or utilize 4 bytes of space. So here's some example integer literals. I've got 16, that's just a decimal number. If I wanted to specify octal, I could preface the number with a 0, so 020 refers to 20 octal. And I can also represent a hexadecimal or base 16 number, and the way I do a literal integer in hex in C is I preface it with a 0x. So here you see a hex 10 literal. We also have support for floating points, and this is the float keyword, and these typically also occupy 4 bytes in memory. And here's some examples. So I have a 0.00225, and I can also use scientific notation to represent floating point numbers in C. We also have a double type, which is an extended precision float. And on most machines today, these will typically occupy 8 bytes. Now, unless told otherwise, when we have literals appearing in our program, they're assumed to be double. So if we want to store a literal as a float, then we're going to put a little f on it. So you can see I put 3.14f. Okay, so if we want to specifically mark something as a float instead of a double, that literal needs to have the f on it. Otherwise, the compiler is going to assume they're doubles. We also have some modifiers that we can use when we define integers and floats. So we can use a long or a long, short, unsigned, and signed. And all of these basically help specify how much space we actually want to have the variable occupy in memory. So on some systems, if we use long on an int or a double, or long, it will extend out the size, so it'll actually use more space. Short, on the other hand, is used to specify you want to use less space. So on some systems, short, if we put short in front of int, it'll actually take half the space. We can also use signed or unsigned in front of int or char, and that basically designates whether or not we're doing signed integers or unsigned. If we put unsigned on there, we typically get another bit of resolution because that most significant bit is not used to represent negative numbers. Now, I mentioned that those modifiers on the previous page sometimes modify because ANSI C doesn't really specify the size that each of these has to occupy. And so you're actually going to find that the size of these intrinsic types in C will vary by the compiler and the machine. But in general, ANSI C does define some rules that help us understand how much space these should occupy with respect to each other. So first of all, ANSI C defines that a short int in terms of size has to be less than or equal to the size of an int, and an int should be less than or equal to the size of a long int. Similarly, for floating point numbers, a float should be less than or equal to a double, and a double should be less than or equal to a long double. Now, if you're wondering on your particular machine and your particular compiler how much space a particular type occupies, C and C++ do define this unary size of operator. And it can be used to determine the amount of size any intrinsic type, union, or struct takes in bytes. Now, we haven't talked about unions and structs yet, but we'll get there eventually. Another thing we might do in C is what we call typecasting. And typecasting is when we as a programmer specifically tell C we want it to handle a particular variable as a particular type. So in my first example here, you'll see I've defined a float f and then an integer I, and I've assigned a 10 to the integer I. Then what I can do is I can promote that integer I to a floating point type by putting the word float in front of I on the right hand of the assignment statement. And that essentially assigns a 10.0 to f. In my second example, I've assigned the floating point variable f the value 3.14, and I could then go and assign that value to an I, but if I put an int typecast in front of that f, it basically is going to truncate everything to the right of the decimal point. And so I'll end up with a value of 3 in I. And it's important to note here, it is not going to do any type of rounding here for us. All right, so that's a really quick intro to the C language. Now let's take a look at some actual code and talk a little bit about our dev environment. With regard to our development environment, we're going to assume that you're running on Linux or Unix. And if you do not have access to a Linux or Unix machine, the quickest and easiest way to get up and running on, for example, your Windows computer is to go over to virtualbox.org, grab yourself a free copy of the VirtualBox virtualization product, and it's a free download. Then go over to ubuntu.com and click on the download link and grab yourself a copy of the Ubuntu desktop. Now what you're going to get here is an ISO image, so a CD or DVD-ROM image, and when you create a Linux virtual machine instance in VirtualBox for the first time, you can give it that ISO image and it will go ahead and boot off that ISO image and allow you to install Ubuntu Linux distribution into the virtual drive that you created there. Now, if you have a good internet connection, you can accomplish this all in less than 15 minutes, and you'll have a full-blown Linux desktop running on your computer. So here I am in my Linux environment, and I'm going to open up a terminal window here. And let's go ahead and write the Hello World program that we just saw in the view graphs. So I'm going to use the VI editor here to do this. If you don't know VI, you can just Google and you'll find all kinds of tutorials on how to use VI. Of course, there's more user-friendly editors as well on Linux. You can use gedit and there's many more. But I'm going to keep it simple. So we'll say VI hello.c, so all of our source files in the C programming language, we're going to give them an extension of .c. And the first thing I'm going to do is put that include standard IO. And once I've done that, I can define my main function, which is the entry point. And we'll remember that it returned an int and it took no arguments. So we'll put void as the function main's input arguments, and then I need the code block. And I'm going to add a single line of code here. You'll recall we used the printf function in the standard IO library, and we had it print hello space world, and then we need to put that escape in to get the line feed to print out, and then close off the function call with my right parent semicolon. And the last thing I needed to do, since my main program returns an int, is I need to return an integer. So I'm just going to return a 0. And at this point, my program is complete. And you'll notice how VI is intelligent. It knows all about C syntax, and it has color-coded everything here for me. So I'm going to go ahead and save it. And now it's time to compile it. So to compile it, I can use the GCC compiler, which is aliased to CC on Linux, but I'll say GCC space and then the name of the source file, hello.c. And this step actually does everything. It reads the source file, processes it, it links it with the runtime library, and if I do an ls now, you'll see there's two files in the directory. There's my source file, hello.c, and there's another one called a.out. And a.out here is showing up as light green in my bash shell, which means its executable bit is set, and we can check that by doing an ls-l, and that is the executable program. And to run it, I'm just going to put /a.out because I don't have my current directory in my working path. And sure enough, it runs hello world. Now, another way we can do this, if we wanted to have the program name be hello, I could actually get rid of that a.out, and I could tell the compiler to compile hello.c, but put the output with a -o into the file hello. When I do this, if I now look at my directory, you'll see a program hello, and I can run it here, hello world, exactly as I did before. Now, there's one more thing I could do here. Let's say I didn't want to type in that -o option. So let me remove hello. So another thing I can do is I can use make. Now, normally with a more complex build with make, we'd have a make file. But make is fairly intelligent, and if it sees a source file, it'll kind of interpolate and understand what we're asking it to do. So without even a make file, if I just say make hello, it looks through my directory and it's going to see, is there a source file that correlates with this target that I'm being asked to build, and if so, then run the appropriate compiler and build it. So if I do this, you'll see that make automatically runs the compiler and does the -o option. So once again, my hello program is compiled and placed in the right place, and all I had to do was type make hello. Okay, this will work on Linux and most Unix machines. If you're developing on Windows, you might have to do some extra configuration to get something like this to work. But anyways, that's a very quick example of how we edit and build a C program with the GCC compiler on Linux.